In this video, we will explore some more exercises about functions and their graphs, polynomial and rational functions. So for the first part is finding the following. First question is find the domain of each. The first function is f of x equal to square root of x minus 1. In this square root of x minus 1, we will follow the rule under the root. And as we know, under the root, this x minus 1 must be greater than or equal to 0. So we will start solving for the domain of f by putting x minus 1 greater than or equal to 0. And solving for x is greater or equal to 1. And we can write this domain in interval notation, which is 1 up to infinity, including 1, but not including infinity. So that is the domain of the first function. For the second function, we have a fraction which is 1 divided by square root of x minus 1. So we will apply the rule in the domain of a fraction or domain of rational function. So we have the numerator which is 1 and we don't have any problem with this. And the denominator is under the root, similar to the first question. But we know the rule under the root, which is x minus 1 must be greater than or equal to 0. But then, since this is in the denominator, so it means to say the domain of f here, so we will set this x minus 1 greater than 0. So we have to remove the 0 in the denominator because division by 0 is not allowed. So solving this inequality, so x is greater than 1. So this is the domain, and we can write the domain as interval notation, which is 1 to infinity, not including 1 and infinity. So this is the domain of this function. Then for the third one, it's a fraction again, which is 1 over cube root of x minus 1. So in numerator, there's no problem because it's a constant, and even a polynomial in numerator, the domain is always all real numbers. And then for the denominator, so we have a function which is a cube root of x minus 1. And as we know, in cube root of x minus 1, since this is an add root, this can be any number. But the problem is, this cube root is in the denominator and there's a rule that division by 0 is not allowed. So it means to say, we can start the domain of f by putting this cube root of x minus 1 not equal to 0. Or you can just write x minus 1 should not be equal to 0. Because if you will take cube of both sides for this, you will get this. So when x minus 1 is not equal to 0, it means to say that x is not equal to 1. So the domain of the function is all real numbers except 1. And then for the last function, so we have a fraction again, which is 1 divided by absolute value of x minus 1. And since we don't have any problem with numerator, let's take a look at the denominator. Remember, when you have an absolute value, the domain here is all real numbers. But then this absolute value is in the denominator and division by 0 is not allowed again. So it means to say the domain of f, we were starting with, this x minus 1 should not be equal to 0. So x is not equal to 1. So the domain here is all real numbers except 1. So if you will notice, in these four functions, these two, even they have the same square root, when we change the position, when we make this as a fraction or we make this square root of x minus 1 in the denominator, they don't have the same domain. But this third function and the fourth function, you can see that when you have an add root and you have its absolute value, we know that the domain are all real numbers. But then, since they are in the denominator, so we have to set that they should not be equal to 0. And then you can see that they have the same domain. So that's for the first question. For the second question, so we have here the problem about difference quotient. And this is the difference quotient where h is not equal to 0. And our given function is square root of 2. Take note that this is square root of 2 even square root. This is a constant. So f of x is equal to a constant function. So it means to say, if we will find for f of 1 plus h, that is still equal to square root of 2. Because for any value of x here that you will put, even you put 1 plus h in x here, the answer is always square root of 2. And then, if we find f of 1, the answer is also square root of 2. So it means to say, if we find for the difference quotient, this is square root of 2 minus the square root of 2 divided by h is 0 over h, which is equal to 0. So the answer here is 0. For the third question, find the value or values of m if the point m2 lies on the graph of this function x cubed plus 1. When you say this point m2 lies on this function, meaning this m2 represents x comma y. So m is equal to x and the y value is equal to 2. So if we will put that point in this function, this y equal to x cubed plus 1, and we know that y is equal to 2, so we can substitute 2 in y, so 2, and then we will substitute the x value by m, so m cubed plus 1. So we will get this equation from that. And solving for m here, m cubed is equal to 2 minus 1, where m cubed is equal to 1. And then solving for m, you will take the cube root of both sides. Cube root of m cubed is equal to cube root of 1. So it means to say the m value is equal to 1. So that is the m value that we need here in this point. So it means to say 1, 2 lies on this graph of the function. So that's for the question number 3. Then for question number 4, here this is about graphing transformation. Let us describe the graph transformation of the given function from f of x equal to square root of x to obtain the graph of the function, which is g of x equal to negative square root of x plus 1 plus 2. So if we will start from the parent function, which is f of x equal to square root of x, and we want to graph, or we want to describe the graphing transformation in this function g, so we can have f1 of x, which is equal to, let us start by replacing this x by x plus 1. So it means to say this is shift 1 left. And then after that, we can multiply this is square root of x plus 1 by a negative. So let's multiply a negative here. Then, after shifting 1 left, this is a reflection about, since it's multiplied in the y value, so it is a reflection about the x-axis. And then after that, we can continue by adding 2. Since we already finished this first term with negative square root of x plus 1, now we can proceed with adding 2. If I will add 2 here, then the next is shifting 2 units upward. So this is now your function g. So we completed your function g based from the parent function f, which is square root of x. So this is how you would describe the graphing transformation from this function to that function. So shifting 1 left, then reflection about the x-axis, then shifting 2 units upward. So that is how you would describe the function. Then for question number 5, write a function whose graph is the graph of y equal to absolute value of x, shifted 3 units, then reflected about the x-axis. So here we are defining a function. So we will write a function based from this. So let us start with y equal to absolute value of x. When you say shifted up 3 units, so the change is in y. So this is y equal to absolute value of x added by 3 because it is shifted up 3 units. And then after that, then reflected about the x-axis. When you say reflected about the x-axis, you will multiply negative 1 in the y. This is your y function. So if you multiply negative 1 in this y value, so you will get y is equal to negative absolute value of x, then minus 3. So you have to multiply in these two terms. Multiply that with negative because this is the y function with two terms. So this is what we want in this question number 5. In this question 6, if f of x has a range of interval negative 2 to 4, then the range of function g, which is negative of f of x plus 1 plus 2, is. So here, we have to take note that this range, it means these are y interval. So here, we will write that y is on the interval from negative 2 up to 4. Take note that these two values here are y values. Then, so let us analyze the graphing transformation here and what should be the first order. So if I will look at this as the first order, you can see that when x is replaced by x plus 1, so this is shifting horizontally 1 unit to the left. To the left meaning the change is in x, but these are the y values. It means to say there is no effect on this interval of y, which is the range. And then after this is we can now move to this negative 1 here. Negative, multiplying negative in the y value. So it means to say when you have a negative in the y value, there's a reflection about the x. And the effect in the function is negative in the y. So there will be effect here because these are y values. So let us try to put, so we will multiply negative 1 in the y. So if we will multiply negative 1 in y, so both of these are y values, so we will get positive 2 and negative 4. But then if you will look at this, since negative 2 multiplying negative 1, it will give us 2. And then this 4, it will give us negative 4. So I will also adopt this close here and then open here. But if you will notice, this interval 2 to negative 4 is not the proper way of writing this because negative 4 is smaller than 2. So it means to say we can arrange this to negative 4 and then positive 2. So that will be the new range after reflection about the x-axis. And then the last transformation is adding 2. When you say adding 2, meaning adding 2 in the y value. So it means to say there will be a change here. There will be an effect in these two y values. So the effect would give us, so here we said we will add 2 in the y. So if I will add 2 here and I will add 2 there, so the new range of the function will be negative 2, comma 4. So this will be the answer for this. Then for question number 7, let this 1, negative 2 be a point on this graph of f of x. What is the point on the graph of h, which is f of x minus 3 plus 2? So let us try to analyze when we say a point. When we say a point, 1, negative 2, this represents x, y. So the first value is x and the second value is y. And then if we will analyze this graphing transformation and we will start from this, so we can see that this x minus 3 is shifted 3 units to the right. So when it is shifted 3 units to the right, we're adding 3 in the x. So let us add 3 here in the x value. And then another graphing transformation is adding 2 in the y function. So adding 2 in the y function means we will add 2 here in minus 2. So adding 2 here. Now, the new point that we are looking for in this graph of h will be 1 plus 3 will be equal to 4, and negative 2 plus 2 will be equal to 0. So we will now have positive 4, 0. The point 1, negative 2 in the function f will be the point for 0 in the function h using this transformation. So the answer is this, 4, 0. Now for question number 8, the question is, how many points of intersection between the function f of x equal to 1 and f of x equal to negative 1 over x? We can show this in two ways. One is algebraically, the other one is graphically. For algebraic solution, so since we know that f of x is equal to f of x, so we can equate 1 equal to negative 1 over x. So we will start from there. Negative 1 over x is equal to 1. And we can write 1 as 1 over 1, and then we can do cross multiplication. X times 1 is x, and negative 1 times 1 is a negative 1. So we will have x equal to negative 1. So you can see that the x value is only 1. It means to say there's only one point of intersection. Now graphically, if you are familiar with the graph of f of x, which is equal to 1 over x, we will graph it in this way. So that is the graph of 1 over x. It's a rational function with horizontal asymptote and vertical asymptote. And then, if we want to graph this negative of 1 over x, so you can see here that we multiply negative in the y. So the reflection is about the x-axis. So this graph here will be reflected on the x-axis. It will be like this. And this graph here will be reflected on the x-axis like that. So now this is the graph of negative 1 over x. This function is now negative 1 over x. And when x is equal to 1, when y is equal to 1, okay, when y is equal to 1, y is equal to 1 is here on this part, and the point of intersection is only 1. So that is the graphical solution to know the number of point of intersection. So there's only one. So you can do it graphically or algebraically. So if the number of x values here, when you solve it, is only one value of x, then there's only one point of intersection. But if there are two x value here, then the number of intersection is 2. So that's for number 8. Then the answer here is this. Then for question number 9, we need to describe the end behavior of the given function negative cube root of x plus 2. You can do this in two ways. One is algebraically, the other one is graphically again. For algebraically, what you can do is, so we have f of x equal to negative x to the power 1 over 3. We know that the power is 1 over 3, but we can assume that this is an odd power. So the leading term here is this term. So it means to say f of x, the leading term is negative x to the 1 over 3. And since we have an odd power, remember when we have an odd power, there are two options. One is the graph, the end behavior will be y is increasing on the right side and decreasing on the left side. The other one is the y is decreasing on the right side and the y is increasing on the left side. Since the coefficient is negative here, so we will choose the second graph. This one. This is the end behavior. Now, let us describe this end behavior. It means to say, when x approaches to positive infinity, y is decreasing. So as x approaches to positive infinity, y approaches to minus infinity because it is decreasing. And then when x approaches to minus infinity, when x approaches to minus infinity, y is increasing. It means y approaches to positive infinity. So this is how you would describe this function. So as we said here, you would just take the leading term. You can try also graphically if you want. Now for the second part, this is a true or false question. So as we answer this as a true or false, so let us write as true with T and false as F. Then as we write the answer with true or false, then we can explain as well. So for the first question of true or false, if the function is increasing function, then f of x minus 1 is also an increasing function. So let's create a given of an increasing function like this. If this is the graph of increasing function, and when we transform this, as you can see here, the x is replaced by x minus 1, meaning it is shifted shifted 1 to the right. So when this function is shifted 1 unit to the right, it will be like this, and it's still, that is an increasing function, meaning this is true. Then for question number 2, it says that if f of x is an even function, then f of x plus 1 is also an even function. So let us create an example of an even function, like the most common of an even function is an absolute value function. So if this is an even function, then f of x plus 1, when you see f of x plus 1, means this is shifted 1 unit upward. If we will shift this graph 1 unit upward, still you can see that this is an even function. So this is again true. For question number 3, the graph of polynomial function of even degree has the same end behavior on both sides. It means to say, when the degree even, when the degree is even, we know that the end behavior when the degree is even is either increasing on both sides or decreasing on both sides. So it means to say this is true. For question number 4, the interval 1, 2, union -2, -1 could be a domain of an even function. So let us try to graph these two intervals. So let's create a real number line with 0 here, then +1, +2, then -1, -2. So 1, 2, closed. And then the other one is -2, -1, close at -2, open at 1. So if this is the y-axis, so can we see that they represent as a domain of an even function? Can we say that this is an even function? When you say even function, this interval should be reflected across the y-axis, but they are not the same. They're not the same because this is closed, but this is open. This one is okay because both of them close, but this one is not the same. So it means to say this is false. To be an domain of an even function, if we will correct this, this must be from -2. So this must be here. The correction is here. This must be from -2 up to -1 closed to make it true. Okay, so that's for question number 4. For question number 5, a polynomial function can have more than one y-intercept. When you have a function with more than one y-intercept, let's say this is y-intercept, then you want another y-intercept, means this is not a function anymore. Why? Because there are two outputs. So this is false. So for us to say that it's a function, there should be only one output, meaning there should be only one y-intercept, not more than one. Okay. Then for question number 6, this function square root of x minus absolute value of x added by 3 is a polynomial function. Remember, the polynomial function is a smooth continuous curve, and the power of the variable in the polynomial function is power 0, power 1, power 2, power 3, and so on. And there should be no negative power, there should be no fractional power. So as you can see here, the first term, we can answer this that this is false. This is not a polynomial function because of this square root of x. Because the power of x here is 1/2, and another one is this absolute value of x. This is not a polynomial function. For question number 7, the graph of the function negative x times x minus 2 squared times x plus 1 touches the x-axis at x equal to -2. When you say touches, means these are multiplicity 2, meaning with even power. There's only one with even power, which is this. And the 0 here is x equal to 2, not x equal to -2. So this is not correct. So this is false. So as we know here, the 0 here in minus x is, the 0 here in minus x is 0 with multiplicity 1. Here the 0 is -1 with multiplicity 1. But here the 0 is 2 with multiplicity 2, meaning it touches at x equal to 2, not -2. For number 8, the graph of the function has a hole at x equal to -1. Remember, the rational function has a hole if there's a common factor. As you can see here, there's no common factor in numerator and denominator. Take note that this x squared plus 1 is not equal to x plus 1 squared. And you cannot factor this denominator. So meaning there's no common factor. There is no hole. So there's no hole here in the rational function, meaning this is false. Number 9, the maximum number of turning points of the graph of this function is 4. So let us identify the degree of this function to know the maximum number of turning points. This function, this is the leading term of this function because the highest power of x here is 6, meaning this function has degree 6. It means to say the turning points is at most less 1 in the 6, at most 5. So maximum of 5. So this is not correct because it says here the maximum is 4. When you say at most 5, the maximum is 5. So this is also false. So that ends the true or false. For part 3 of this exercise, let f be equal to this rational function and let g equal to this another rational function. So for the first part, we find the domain of f over g in interval notation, and the second part, find the quotient f of x divided by g of x in its simplest form. So here, in finding for the domain of f over g, let us recall the formula. Domain of f over g is equal to the domain of f intersect with the domain of g minus all the x values that makes g of x equal to 0. So you have to follow this one by one and find this one by one. Let us start with the domain of f. For the domain of f, we can see that the function is a fraction. And in this fraction, we have to take a look in numerator and denominator. In numerator, there is a square root of x. And in this square root of x, we know that there's a rule under the roots. And the rule is that x must be greater than or equal to 0. So that is for the numerator. And then for the denominator, we can see that this x minus 2 is a polynomial. So it looks like the domain is all real numbers. But then, since this x minus 2 is in the denominator, and this cannot be 0, so we will say, but x minus 2 cannot be 0. So if we will solve this, x is greater or equal to 0, but x cannot be 2. So if we will try to graph that, the 0 and 2 open at 2, close at 0, it says that x must be greater than or equal to 0, but not including 2. So this is the domain of your function. So the domain is from 0 to 2, union from 2 to infinity. Now, let us proceed with the domain of G. For the domain of G, we can see that G is a fraction with x minus 1 in numerator and x minus 2 in denominator. Now, let's take a look at the numerator first. Since the numerator is x minus 1 and this can be 0 or any real number, meaning to say this is a polynomial function and the domain here is any real number, so there is no problem with numerator. Then for the denominator, even this is a polynomial whose domain is all real numbers, but take note again that this x minus 2 cannot be 0. So it means to say that the domain of G is all real numbers except 2. Then for the third part here is, so we are done with the domain of F, we are done with the domain of G. So next is, we have to write g of x equal to 0. When g of x is equal to 0, so let us find that. G of x equal to 0 means we are solving that x minus 1 over x minus 2 equal to 0. And we can find that x minus 1 is equal to 0 or x is equal to 1. So we have to remove this one in this interval because we have to remove the value of x that makes g of x equal to 0, and that x is 1. So now, getting the intersection of these two and then removing the x value that makes this 0, so we will get the domain of f over g, which is, so if you will look at this number line and removing 2, we already removed the 2, we will still remove 1 because g of x is 0 when x is equal to 1. So it means to say your domain of f over g is starting from 0, then open at 2, and also open at 1. So the domain is from 0 to 1, 1 to 2, and 2 to infinity. So writing this in interval notation, we will write as 0 to 1, union, from 1 to 2, union, from 2 to infinity. So this is the domain of f over g. Then, for letter B, let us find for f of x divided by g of x. So f of x is the square root of x over x minus 2, and g of x is x minus 1 over x minus 2. So we have a fraction divided by a fraction, so we have to change the operation to multiplication, multiplying the reciprocal of this denominator, which is x minus 2 over x minus 1. And then we can now cancel this x minus 2 because they are common. So f over g is only simply square root of x over x minus 1. So this is the answer, the final answer in the simplest form, because we cannot simplify this anymore. Now let's have another question similar to the previous question. Finding the domain of f over g and finding f over g given the two functions, which are both of them are rational function. So here in finding the domain of f over g, if we will recall, the domain of f over g is the domain of f intersection with the domain of g minus all the x values that makes g of x equal to 0. So first, let us find the domain of f. For the domain of f, if you will look at this, it's a rational function. And there's no problem with numerator because this x plus 2, it's all real numbers. What the problem is in x minus 1 because x minus 1 cannot be 0. So it means to say the domain of f is all real numbers except 1. Why 1? Because the x value that makes the 0 is at 1. And then for the domain of g, if you will look at the g, The function g is a fraction again, and numerator doesn't have any problem because you can put any number here because it's a polynomial. But the denominator, this cannot be 0. So if we will solve that x squared minus 1 is 0, so x squared is equal to 1, and x is equal to positive and negative 1. So it means to say the domain of g is all real numbers except positive 1 and a minus 1. So the value of x here that makes it 0 are these two values, so we have to remove that. And then for the last one, for the third part, is this. Don't forget this because you have to exclude all the x values that makes this g of x equal to 0. So g of x equal to 0. So we need to know what is the x value that makes g of x equal to 0. When you say g of x equal to 0, x squared plus 2x over x squared minus 1 is equal to 0. And take note, if you're solving this equation, you can write 0 as 0 over 1, and you can do cross multiplication like this. Or you can analyze that this fraction is 0 only if this numerator is 0, because as we know, denominator cannot be 0. So this means if you will solve this, it is enough to solve that x squared plus 2x is equal to 0. And solving this kind of quadratic equation, you will factor out the x to get these factors, and then x is equal to 0 and a minus 2. Take note, we have to remove all the x value that makes g of x equal to 0. And what are those? 0 and a minus 2. So we also have to remove this. So now, getting the intersection of this, all real numbers except 1, all real numbers except 1 and minus 1, and you will also remove 0 and minus 2. It means to say that the domain, therefore, the domain of f over g is all real numbers except 1, minus 1, 0, and a minus 2. So this is the answer. Now, for f divided by g, f of x divided by g of x, so you are dividing two fractions, x plus 2 over x minus 1 divided by x squared plus 2x over x squared minus 1. So division of two fractions again. So you can change the operation to multiplication. So we have x plus 2 divided by x minus 1 times the reciprocal of this, which is x squared minus 1 over x squared plus 2x. Then you can simplify this answer by factoring this part. So let us try to factor. X plus 2 divided by x minus 1 times the factors of this is x minus 1 and x plus 1, and the factors for this denominator is x times x plus 2. Now, try to see the common factor and canceling them out. So x plus 2 cancel with x plus 2, x minus 1 cancel with x minus 1. So the final answer is x plus 1 divided by x. So this is your f over g. Take note, you cannot cancel the x in this answer. Canceling x is not correct because there is plus 1 here. You have to add one first in x before dividing by x. So that's why it is not allowed to cancel the x here if there is an operation with plus and minus in between. So that is for this question. Now for the fourth problem, the given is piecewise defined function given with three equations. Then we will find the following. So first is finding the domain. You can easily get the domain if you will draw it in the real number line first. So you can write minus 2 and then 1. So we have minus 2 here and then positive 1. For the first equation, the domain is only negative 2. So meaning I have to shade minus 2. Only minus 2. And then the second domain is from minus 2 to 1, not including minus 2. So minus 2 to 1. So I have to make 1 open because it's not included, But I will not make minus 2 open because it's included here on the first equation. So the graph is this, from minus 2 to 1. Then after that, for the third domain is x greater than 1. When you see x greater than 1, not including 1, but more than 1. So I have to continue shading this on the right side of 1. So as you can see here, it's very clear that the domain, you will write this as starting from minus 2 up to 1, open at 1, then union from 1 to infinity. So that is the domain. Then to find for the x-intercepts, we have to set y equal to 0, and this y is f of x, meaning you have to place this f of x by 0 and equate that or solve the three equations. The first equation is 4 equal to 0, the second equation is x squared plus 1 equal to 0, and the third equation is square root of x minus 2 equal to 0. So let us solve one by one. In the first equation, 4 equal to 0, since they are not equal, you cannot find any x-intercept here. For the second equation, with this domain, this is the domain, so if I will solve here, x squared is equal to minus 1, and it looks like there is no solution again here. You cannot find x value here, meaning there's no x-intercept here. Why? Because you cannot find x here. If you will square, the answer is a negative number, because squaring x is always a positive number. So there's no x-intercept on the second equation in the first equation. For the third equation, the domain is x greater than 1. So let's see. If we will solve this, square root of x is equal to, moving negative 2 on the other side, it will give us positive 2. And then squaring both sides, because we're solving the equation, so x is equal to 4. Now we have to check if this 4 is in this domain, and it is. So meaning I have to accept this x value as the x-intercept. Therefore, the x-intercept is x equal to 4. Or you can write this as 0.4, 0. So you can just choose either one of that, x equal to 4 or 4, 0. So that's for the x-intercept. For the y-intercept, we have to set x equal to 0. Since we know that x is 0, we have to find out which equation you should use here. Meaning, in solving for the y-intercept, you will only use one equation, because as we know, y-intercept, it should be only one output for the graph or for any relation to be a function. There should be only one y-intercept. So where is x equal to 0? X equal to 0 is in this interval, and the equation is x squared plus 1. So you will only use the second equation. So y is equal to x squared plus 1. So since we put 0 in x, so we have 0 squared plus 1, so y is equal to 1. So this is the y-intercept, or 0, 1. So that's for letter C. Now, let us try to graph. So first, we can try to graph the first equation. Look at the first equation. The first equation is when x is equal to minus 2, the y value is 4. So meaning it's a point. Minus 2, 4. Minus 2, positive 4. We will graph a point or plot a point. Next, the second equation, it looks like it is a parabola, square function with 1 unit up. Remember, the square function is like this, and then we have to move 1 unit up, so it should be like that. So the domain or the graph of this parabola is only starting from negative 2 up to 1. If we substitute negative 2 in the x, because we have to start with the endpoints, if we substitute negative 2 in the x value, we will get the y value as 5. So negative 2, 5. Negative 2, positive 5. So I will make it open. And then after that, when x is 0, remember when x is 0, we get the y-intercept, which is 1. So 0, 1. And then when x is minus 1, maybe we can get the value of when x is minus 1. When x is minus 1, minus 1, y is 2. And then when x is 1, so that's the last number. When x is 1, y is also 2. And I should make this open. Now connecting this, okay, that's the graph of the parabola on the second equation. Next, the last equation is square root of x minus 2. So this is the radical. The radical is like that. Okay, so square root of x minus 2, meaning if the square root of x is like this, moving 2 units downward. So let us start by putting 1 in x. If I will put 1 in x, square root of 1 minus 2 is a minus 1. So 1 minus 1. 1 minus 1, 1 minus 1, and I have to make it open. Next, so we have 1 minus 1. Next value of x that I can put, since this is square root of x, let us try 4 because it's easy to put 4 in square root. So square root of 4 is 2. So we have square root of 4 minus 2. So when we have 4, the answer is 0, 4, 0. And I guess that's it. We can now connect this. Oops. Connect this using a curve like that. That's it. This is the graph of the third equation. So you can see here that we can verify what we solve on letter B and letter C. Remember that on letter B, we solved that there's only one x-intercept and there's y-intercept at 1. So we can check the y-intercept is correct, which is 4, and so this is the x-intercept, which is 4, and the y-intercept is 1. So algebraically, our answer in C and letter B, it matches this graph. So that's the graph of this piecewise defined function. The next question is about rational function. So in this rational function, we will find the equation of the vertical asymptotes. But before that, let's take a look if there's a common factor in numerator and denominator. So it's better if we will factor the numerator and denominator. So the common in numerator is 2, so let's factor out 2. And then the other factor is x minus 1. And then factoring the denominator, it will give us the product of two expression with x and x. And then we need the factors of minus 2, 2 and 1. Since the middle term is a minus, so we have to put the minus on the larger number and positive on the smaller. So make sure that the factors are correct before you continue. So this one, it should be, the product must be this. So you can see that there is no common in numerator and denominator, meaning there's no whole in this rational function. So we can directly get the vertical asymptotes, which are the zeros of this denominator. So the vertical asymptote appeared when the denominator x minus 2 and x plus 1 equal to 0. And the value of x here is equal to 2 and x equal to minus 1. So these are the two equations of the vertical asymptotes. Take note, you have to write the vertical asymptote as an equation with separate equations. So note that in writing for the vertical asymptotes, do not write the following. For example, sometimes students are writing that vertical asymptotes are 2 and a minus 1. So never write in this way. Another one is sometimes the students are writing as the vertical asymptotes are x equal to 2 and a minus 1. Do not write the equation of two vertical asymptotes in this way. Okay, so these two are not correct. Next, to find for the equation of horizontal asymptotes, this is identified based on the degree of this rational function. So for the numerator, the degree is 1. For the denominator, the degree is 2. So since the degree of the numerator is less than degree of the denominator, therefore the horizontal asymptote is y equal to 0. So this is the horizontal asymptotes. And as a note again, never write that horizontal asymptotes is equal to 0. This is not correct. Okay. Then for letter C, let's find the x-intercept. To find for the x-intercept, we set y equal to 0. So it means, so 2 times x minus 1 divided by x minus 2 times x plus 1 is equal to 0. And we know that this fraction is 0 only if this numerator is 0, because denominator cannot be 0. So it means to say we have 2 times x minus 1 equal to 0. So x minus 1 equal to 0, because you can divide both sides by 2. So x is equal to 1. So this is the x-intercept, which is 1. And then for the y-intercept, we set x equal to 0. So substitute in the function 2 times 0 minus 1 over 0 minus 2 times 0 plus 1. So we will get the value of the numerator is a minus 2. Denominator is also minus 2, which is equal to 1. So y is equal to 1 is the y-intercept. So for letter E, so we are done with asymptotes and intercepts. For letter E, we will use the zeros of the numerator and denominator to determine where the function is above, meaning f of x is greater than 0, or the function is below the x-axis, meaning f of x is less than 0. So to find the zeros of the numerator and denominator, we are considering the x-intercepts for the 0 of the numerator and the vertical asymptotes for the zeros of the denominator. And they are, so we will just collect the vertical asymptotes with 2, minus 1, and a 1. So these are the zeros of the numerator, which is 1, and the zeros of the denominator, which are 2 and a minus 1. So 2 minus 1 and 1. 2 minus 1 and 1. So let us write this in the real number line. Minus 1 is the smallest, then next is 1, the next is 2. Then let us find a number on this interval, let's say 3. So let's solve for f of 3. So for f of 3, if we will substitute 3 in the given function, the given function is, I think it's better if we will write the given function. So let us write here. Okay, so f of 3, if we will substitute f of 3, so this is equal to 2 times 3 minus 1 divided by 3 minus 2 multiplied with 3 plus 1. So let's check the value so we can use in graphing. So this is 2 times 2 is 4. So we have the numerator, which is equal to 4. And then denominator is, this is 1 and this is 4 over 4. So 4 over 4 is equal to 1. F of 3 is positive. So we know that the sign analysis here is positive here. And since we can see that all the powers here are odd, so this is minus, this is plus, and this is minus. But you can also check by selecting a number here and then put in the function, then check the sign. Selecting a number here like 0, then put in the function, then check the sign if it's positive. Or selecting a number here, put in the function, then get the sign and check if it is a negative. Okay? So now we can now write here that in letter E, to answer the problem, f of x is greater than 0 on the intervals. So you will select this interval and that interval. So let us write that as minus 1 to 1, and another one is 2 to infinity. And then the other one is f of x is less than 0 on the intervals negative infinity to minus 1. And then another one is positive 1 to 2. So now let us try to sketch the graph using this information. Let us start with the vertical asymptotes 2 and minus 1. Vertical asymptotes x equal to 2. So I'm writing this as x equal to 2 and x equal to a minus 1. X equal to minus 1. And then after vertical asymptotes, we can now graph the horizontal asymptote, which is y equal to 0. Y equal to 0 is x-axis. So this is y equal to 0. And then next is x-intercept is 1 and y-intercept is 1. X-intercept is 1 and y-intercept is 1. As you can see here, since x-intercept lies on the horizontal asymptote, it means to say that this rational function intersect the horizontal asymptotes. So then after that, now we can apply the sign analysis. So let us start when the interval is 2 to infinity. 2 to infinity, the graph is above, and the above is this part, this part. So the graph is there. So select a number at this, let's say 3. We know that f of 3 is 1, so we can choose a point here so that we can connect the curve at this point, then asymptotic in this vertical asymptote and asymptotic on this horizontal asymptote. So that's it. Then after that, for the interval 1 to 2, it should be below. 1 to 2 is on this part. It should be below. So as you can see here, so you will connect at this point and then asymptotic on that part. So it will be like this. So let's connect in this way. And then after that, next interval is from -1 to 1. -1 to 1, it must be above. -1 to 1, it must be in this area. And it's correct because there's the y-intercept is there. So it looks like from this point connecting on this y-intercept and then asymptotic here. So this will be the nature of the graph. So let's connect this in this way, like that. And then the last interval is from -infinity to -1. It should be below. -infinity to -1, it should be below. So the graph must be here. Since there's no point here, so maybe we can try to have an extra point. So let's try an extra point. Like an extra point here is -2. F of -2. If we will solve for f of -2, substituting here, -2. So we have y is equal to 2, x is -2, then -1 over -2 -2. And then here we have -2 plus 1, just to get an extra point so that we will know where to pass the graph. So it's +2 times -3 over -4 times -1. So we will have the -6 over +4. So this is -6 over 4. So it will be -1 point something. -1 point something. So here it's when the x is -2, it's -1 point something. It should be here. -1 2/4 here. Okay, so I think this is -1.5. -1.5. There. The point is there. So now we can now connect. Why there's a 5 here? We can now connect. So this is -1.5. Okay. So we can now connect this. We can now connect this point asymptotic on this horizontal asymptote and asymptotic on this vertical asymptote. So let's connect in this way. Stop this and then like that. Okay. So make sure that you will graph the vertical asymptotes and horizontal asymptotes as a broken line and graph the x-intercept and the y-intercept, and make sure that you will, it's better if you will have an extra point connecting the curve, extra point connecting the curve, and then you can see that the graph is a smooth curve. There's no straight line. And lastly, make sure that all the endpoints here are with arrows. Okay, there should be arrows. Okay, so that's the end of this question. Now for the last problem, let's analyze the graph of the polynomial function given as this. So first, let us find the x-intercepts. So in finding for the x-intercept, we have to set y or f of x equal to 0. So negative 2x multiplied with x plus 1 squared equal to 0. So first is negative 2x equal to 0, and then dividing both sides with negative 2, so x is 0. Next is in x plus 1 squared, we will just ignore the power 2 because x plus 1 equal to 0, we will get x equal to minus 1. So these are the two x-intercepts. And then for the y-intercept, so we set x equal to 0. So we substitute 0 in x, negative 2 times 0 plus 1 squared. Since this is 0 times any number is always equal to 0. So y equal to 0 is the y-intercept. Then for letter C, find the zeros of the function and their multiplicity. The zeros of the function are those values in the x-intercepts. So we can say that zeros of the function are the x-intercepts. And these are 0 and minus 1. And then when you say multiplicity, multiplicity is the power where the 0 comes from. So for example, this 0 comes from negative 2x, and this power x, the power of x is 1. So it's multiplicity 1. So meaning the 0 which is 0 appeared once because it comes from a factor which is x power 1. And then for the 0 which is minus 1 comes from the factor x plus 1, and this appeared twice, so multiplicity is 2. If the multiplicity is 1, it means that the graph crosses in the x-axis, and when the multiplicity is 2, it means that the graph touches on the x-axis. So that's how you will write or identify the behavior of the function based from multiplicity and crosses and touches. And then for letter D, we need to find out, so I just copied the given again here. So we need to find how many number of turning points. Since we have a given function and we can identify the degree, so let's identify the function behaves like, so we do not need to expand this to get the degree. So we can have this term, this is the first term, and this is the second term. On the first term, there's only one term here, which is minus 2x. So I can copy minus 2x and then times. On the second term, squared of x plus 1, the leading term here is x power 2. So we can have x power 2. So we can see that the power function or the leading term of this given function here is negative 2x power 3. So we can see now that f has degree 3. So it means to say the number of turning points is at most n minus 1. At most, subtract 1 in the degree 3, so at most 2. So this is the answer. Then let us describe the end behavior of the graph of the function. So the end behavior, so we can make use of this. Since the function, the leading term is negative 2x power 3 based from this, then we can check that since the degree here is an odd, and the coefficient is, leading coefficient is a negative, we know when the degree is an odd and leading coefficient is negative, the end behavior looks like this. So we can describe it as x approaches to positive infinity, the y approaches to minus infinity because this is decreasing. And then as x approaches to minus infinity in this way, here on the left side, so you can see that the y is increasing, meaning the y approaches to positive infinity. So this is how you will write your answer in the end behavior. And then for letter F, let us use the zeros to determine the function is greater than 0 or less than 0. So this is sign analysis. So if we will collect the zeros again, the zeros are 0 and a minus 1, 0 and a minus 1. So let's put it in the real number line. This is minus 1 and this is 0. So let's get the number here, which is 1. So f of 1. if we will substitute 1 in the given function, where's our function again? So let us write f of x is equal to negative 2x times x plus 1 squared. So I think it's better if we will check. Okay, so f of 1. So f of 1 is negative 2 times 1, and then 1 plus 1 is 2, 2 squared. So the answer here will be 4 times negative 2 is negative 8, negative 8. So we can say that f of 1 is less than 0. It means to say it's negative on this part. And then let us check the power or multiplicity. When the 0 is minus 1, the power is even. Minus 1, the power is even. So meaning it touches here. And it crosses on this part. So as we know, when it crosses, the graph crosses at the 0. So if this is a minus, it means that the left side is a plus. And then since the 0 it touches here, so if this is plus, the left side will be the same sign, which is plus again. So let us now sketch the graph of the polynomial function. Let us start with the x-intercept 0, negative 1, 0, negative 1, 0, and a negative 1. And then after that, we have the y-intercept, which is 0. It's same with the x-intercept. Then as we can see, it says that it crosses at 0 and touches at minus 1. Touches like a parabola. It crosses at 0, crosses at 0. So we have a negative here, negative, positive, and positive. It says that it crosses at 0, crosses at 0, because the power is 1, so meaning it will cross like a line, and then wait, and then it touches at minus 1. Since it's above, it will be like this. Okay, so let us connect. And hold on, what is our y-intercept? Y-intercept is 0. Okay, so I guess it's better if we will get the value. We will get the value at in between. We can get the value in between of this, like negative 0.5. So for an extra point, if you want, you can put f of negative 0.5, and you can put in this function. Okay, so you will know how high the graph will reach. So if I would just graph or sketch the graph of this function, I will continue like this, and then maybe like this. Oh, no, it should be, that's it. That's the graph of the given function. Okay, that's the end of this problem. That is the end of this video. If you find this video useful, please like and subscribe and turn on the notification bell so you never miss out on the future content.